Before we solve logarithmic equations, we first must cover some basic logarithmic properties here in section 5.4.3. Each of the properties that we will cover will be reminiscent of rules of exponents that you already know. In fact, connecting these properties back to the rules of exponents that you already know will help you to better understand these properties. The first one is called the product property. Looks something like this. Log base A of x times y. Now, in this expression, both x and y represent positive numbers. The base A is positive and cannot be equal to 1. If we have the logarithm of a product, we can expand it as the sum of two logarithms. This becomes log base A of x plus log base A of y. So each factor from the original argument receives its own logarithm. Notice we have taken multiplication between the arguments in this position and translated it to addition in a different position. This might remind you of the rule of exponents. When we're multiplying like bases, we add the exponents. That is, we translate the multiplication in one position, in this case between the bases, into addition in a different position, that is, in the exponent position. So essentially, these two rules are one and the same. One is written in exponential form, the other is written in logarithmic form. Remember, a logarithm represents an exponent. Now, if when we're multiplying in the argument, we translate that into the sum of two logarithms, what do you suppose we're going to do if we have a quotient in the argument of a logarithm? A quotient will turn into the difference of two logs. So this becomes log base A of x minus log base A of y. So once again, we're taking an operation here, division, in the argument position, and we're expanding this as the difference of two logs, or we're translating it into subtraction in a different location. In exponents, we say when dividing like bases, we subtract the exponents. So in this case, we take division between the bases and convert it into subtraction between the exponents. In the quotient property, we have the difference between two logarithms, which represents the difference of two exponents. The last property looks something like log base A of x to the mth power. We can rewrite this as m times log base A of x. So if our argument has an exponent, we can move that exponent down in front as a coefficient. This reminds us of a power raised to a power property. When we have this situation, we multiply the powers. So essentially, we are dealing with successive powers. And that's what we have over here. Remember, a logarithm represents an exponent, and m was an exponent, so we have the product of two powers. When we apply the properties in this direction, we call that expansion. And when we apply the properties in this direction, we call that condensing. So these are the three basic rules that we will use to expand and condense logarithmic properties. There are no other properties that we can apply. So keep in mind, we're only learning how to do three things, so limit yourself to doing these three things only. Watch out for this pitfall. It's going to be tempting to take something like this, log base A of x plus y, and rewrite it log base A of x plus log base A of y. That feels natural. It feels like we have distributed a logarithm. However, remember, the logarithm is not a factor or a multiplier. It's the name of a function, so it cannot be distributed. So make sure you understand that is not a true equality. If we have the sum of two logs, like we do here, we would condense it into the log of a product, not the log of the sum. Let's practice these properties on the next few examples. Example 3, expand using the properties of logarithms. Write the answer without using exponents. So notice on example A, we have log base 2 of xy squared over z cubed. The first thing we're going to deal with here is the quotient rule. We've got the logarithm of a quotient, So we're going to separate this as logarithm of the top, logarithm of the numerator, minus logarithm of the denominator. And we'll keep base 2 throughout the problem. So this becomes log base 2 of xy squared minus log base 2 of z cubed. Now notice on the first logarithm, now we're dealing with a product. So we need to take our product rule and expand that logarithm. The logarithm of a product becomes the sum of two logarithms. Each factor is going to get its own logarithm. So log base 2 of xy squared becomes log base 2 of the first factor x plus log base 2 of the second factor y squared. And then I'll copy down the log base 2 of z cubed. Now remember, we're dealing with superscripts and subscripts, so be careful how you write it. The way you write it does affect the way you think about it. The base of the logarithm should be just below the baseline, and your exponents should be superscripts. They should look like exponents. Now, we want to make sure and write our answers without any exponents. And at this point, we still have a couple of exponents. So using our power property, we can take the exponent on the argument down in front as a coefficient. So this exponent's going to move to coefficient position, and this one as well. This gives us log base 2 of x plus 2 log base 2 of y minus 3 log base 2 of z. Now, how do we know when we're finished? Each argument is singular. It is not being multiplied by anything. There's no quotient. There's no power. So since there's no operation in the argument and no exponent, this has been completely expanded. So this example used all three of our logarithmic properties. But if you can learn to see the big picture, this gets easier as you practice. So let's look back over our answer. Notice each of the original factors in the problem got their own logarithm, right? And every factor that came from the numerator ends up with a positive logarithm. The factor from the denominator ended up with a negative logarithm. If you can remember that pattern, that will help you to easily expand something like example B. We have log base A of 5 squared x to the 6th divided by y cubed times w. So we're going to expand this a little more efficiently now that the rules are more familiar. We know that each individual factor in the argument is going to get its own logarithm. If the factor comes from the numerator, we're going to give it a positive logarithm. And if the factor comes from the denominator, we will give it a negative logarithm. It's going to look something like this. Log base A of 5 squared plus log base A of x to the 6th. So notice each factor from the numerator got a positive logarithm. Now, each factor in the denominator is going to get a negative logarithm. So we have minus log base A of y cubed minus log base A of w. Whoops. There we go. Now, the only thing we have to do is move the exponents. So every single exponent is going to move to the left as a coefficient. We end up with 2 log base A of 5 plus 6 log base A of x minus 3 log base A of y minus log base A of w. Each argument does not contain any sort of operation or power, so it has been completely expanded. So again, try to see the big picture. Look at the original condensed logarithm. Each individual factor now has its own logarithm, and the factors that came from a numerator ended up in a positive logarithm, and the factors that came from the denominator ended up in a negative logarithm. All of the exponents have moved down to coefficient position, so that logarithm has been completely expanded. Now let's go backwards. This time we're going to start with an expanded logarithmic expression and condense it to a single logarithm with no coefficient. So just like on the previous example, the very last step was to move the exponents. We're going to make that our first step on this problem. each coefficient is going to move to the exponent position. So we could rewrite this as log base 2 of x cubed minus log base 2 of y squared plus log base 2 of z to the 5th. Then we're going to condense this to a single log base 2 of some argument. Now remember, if the argument comes from a positive logarithm, that factor will end up in the numerator, right? If the argument comes from a negative logarithm, that factor needs to end up in the denominator. So continuing this logic, z to the 5th, since it comes from a positive logarithm, is going to land in the numerator. So we have in our numerator x cubed, y squared lands in the denominator, and z to the 5th ends in the numerator. Our logarithm has a coefficient of 1, so it has been completely condensed. Now, I do want to point out one thing. Notice the operation between the x cubed and the z to the 5th is multiplication. Don't be tempted to put a sum right there. Everything in the argument will be either multiplied or divided. Okay, let's practice one more, and then we'll see how these properties will be important in solving logarithmic equations. The first step in condensing is always to clear your coefficients. The coefficients will move to the exponent position on the arguments. So we end up with log base 2 of 3 squared plus log base 2 of x to the 6th minus log base 2 of w to the 4th plus log base 2 of z. Just want to remind you that I always enclose the argument in parentheses. You do not have to enclose the argument in parentheses, but keep in mind your calculator will always enclose it in parentheses. So it kind of helps to understand that the argument is distinct from the function name log. Now that we have moved the exponents, we can condense to a single logarithmic expression. We just have to decide where is each factor going to land. If the argument comes from a positive logarithm, that argument will end up in the numerator. Positive means upstairs, so arguments that come from a positive logarithm land upstairs. Those that come from a negative logarithm end up downstairs. So we can condense this very efficiently. Let's call that 3 squared a 9. We'll go ahead and evaluate that. We get 9x to the 6th, w to the 4th in the denominator, and z in the top. So we have completely condensed that logarithm. Now, those are different than what we've learned before, so it is going to take some practice, but keep in mind these will be important for solving logarithmic equations in the next section.